Okay guys, welcome to another video about VR in Godot. We're going to have a look at the OpenVR GDnative module that we're working on, which is well, pretty much finished at this point in time. So yeah, it's actually quite fun to play with a little bit. Notice that I'm recording this on my Mac because my copy of OBS is misbehaving on my Windows machine. But everything that I'm doing right now, I have done on Windows. So the recordings that you see from some of the in-game footage will all be recorded on my PC. In theory, the OpenVR module should work both on Linux and on macOS. I don't have a Linux setup, so I can't confirm that. I know some other people have been playing with it and giving me some feedback. So as far as I'm aware, it works on a number of systems. For macOS, my Mac simply isn't powerful enough to run VR. Not to mention that. As far as I'm aware, there currently aren't any drivers for the Oculus Rift that I'm using. So I'm stuck on my little Windows machine. Obviously, with using a Rift and touch controllers, we are not yet talking directly to the Oculus SDK. That is something that I'm looking into, whether we can support that as well. But at this point in time, we're going through the OpenVR system, which so far seems to be working pretty well for both the Vive and for the Oculus Rift, and in theory should work for quite a number of headsets. But anyway, for this video, I'm going to be looking at the demo game that I'm working on for this series, and just going through some basics, and then making a first start at some really basic locomotion. So we'll be just looking at this demo project that I've made, explaining how I've set up a few things. And how this basically all fits together, and I hope to make this a bit of a series where in each video we start looking at a different topic. The first thing to have a quick look at, I'm probably going to zip this up and put this on my Dropbox and put a link down below so you can download and try this yourself. But it's important to know where certain files go. Now, like I said, this is a Windows build that I'm actually working on, so we're looking at the files as they would be on a Windows machine. And there are a couple of things that are important. The first is that next to the Godot.exe file, we need to place the OpenVR API DLL. This is the DLL supplied by Steam as part of the OpenVR SDK, and is the library with which Godot ends up talking to the Steam VR platform. The other thing that we need is this bin folder, and all the files that are contained within. Now, we're not sure yet if that is going to be the final structure. We're probably going to be pushing this out either through the what's the thing called, the asset store that Godot has. So the final location might change. For now, it is in this bin folder, and you will find 3 files here that are important. The first is another DLL, which is the GDnative plugin itself. So this is the code that we wrote in order for Godot to talk to the OpenVR system. The second file is this resource file, which is a file that Godot can load, and it contains information about which dynamic libraries it needs to use. So for instance, if this would be a Linux install, there would be a Linux version of this dynamic library. If this, obviously if I got this working on my Mac, there would have been a Mac version of this library. And in this OpenVR.tras file, you would find the names of all those files so that Godot knows which ones to use for the individual platforms. The last file that's in here is this GDNS file. GDNS file is another file format that belongs to GDnative. And this allows us to bring in meshes that are published by OpenVR. So every platform that is supported by OpenVR, or every vendor that makes drivers for OpenVR, will also provide 3D models for their controllers and 3D models for their headsets. And OpenVR will make those available to us through this render model interface. And we've made that available inside of Godot. So it's a nice, quick and easy way to bring in, say, a controller mesh into your game. But they are static message, so they don't react to controller inputs like buttons and axes and that sort of thing. But still, you know, it gets you going, which is quite nice. Other than that, all the other files, obviously, in this folder structure are just the normal files that are part of our game, and we'll have a look at those from inside the Godot editor. So by default, we obviously open up our main scene, and that contains all the basic parts of our system that we of our game that we need. I've just created this little simple little level. Sorry that the frame rate is really slow. OBS is for some reason really taking a lot out of my my poor little Mac. But as you can see, you know, this is just a really simple little world that I build. Just a little grass field with tables and trees, and we'll start having some fun with that as this demo slowly gets built up. Now, in our scene node list, we have a number of things that are important. The first one that I want to talk about is this player origin subscene. For those who have seen my earlier videos about setting up the AR/VR origin and AR/VR camera, in this setup I have actually moved that into a subscene, which just makes it easier to maintain. So there's not much in here except for that AR/VR origin root node that we need for all our VR implementations. We have our AR/VR camera as a subnode there, which sets up the stereoscopic rendering and is automatically tracked as you move around the environment. And we have two controllers, one for our left hand and one for our right hand. I won't go into the controllers too much in this video today. I want to leave that for the next video where we're actually going to be doing something with these controllers. There's also a script on the player origin that we'll look at in more detail in a moment. The other thing in our main scene is just a little FPS counter. There's some shapes for the floor. Again, in this video, we won't really do anything with that yet. We've got some objects that we'll be adding into the scene that we'll be able to interact with. But again, that is for the next video. And that's basically, in a nutshell, our current setup for this environment. I've also set up a world environment just for our lighting and things like that, and it just has a standard panoramic sky in the background, which somewhere around here should have a sun. We'll see that in a minute when we actually are in the game itself. Let's have a little look at the script that is on the main scene. And this really only has a few things that again should be familiar if you looked at the earlier videos that I did on the mobile VR introduction. With the only difference that we are grabbing in this case our OpenVR interface, and if that is found, we will initialize it. And if we are able to initialize it, we will be putting AR/VR to true on our main interface, and we're going to turn HDR off. Now that's an interesting one. This is one thing that I haven't found a workaround for, and I'm also not entirely sure why OpenVR has a problem with this. In its full glory, Godot now has a full HDR render buffer to which it renders your whole scene, which gives it the ability to do a whole bunch of nice effects with lighting and stuff like that. The problem that we have is sending that buffer to OpenVR simply doesn't work. OpenVR will not accept that type of texture buffer. This doesn't work. So the only option that we have right now, and it feels a bit like a workaround at this point in time, is to turn the HDR buffers off, to just use a normal 8-bit per channel color buffer, and render to that. I think it's all got to do with throughput and the simple fact that there is a performance penalty in the bigger buffers, but I don't know. Anyway, for now, that is the only kind of drawback that we have, that you have to turn HDR off in order for OpenVR to work. The last thing that is new that wasn't in the mobile VR demo is that I'm changing the window size of the application to half the recommended render target size. Now that's an interesting one. One of the things that the mobile VR solution did was that we actually rendered directly to screen, and that was because the screen of your mobile device was the screen that was used inside of your headset. And with OpenVR, that's not the case. With OpenVR, we render the two images for each, or the image for each eye, and we actually send that off to OpenVR, and OpenVR will display that on the headset that is attached to the computer, which leaves our main screen available for us to use. Now, by default, what the OpenVR GDnative plugin does is render out a copy of the left eye buffer to screen, so that people who are looking at the person playing in VR can see what's going on screen. You can stray away from that. Again, that's going to be a topic for another video where we're going to look at doing something alternative on the main screen. But for this demo, we are going to keep using that left eye preview. The thing is, because of the way that VR works and the way that the lenses work and the way that we render a distorted image to screen to deal with the lens distortion effect that happens with the lenses that the VR headsets use, we're actually rendering our left eye and right eye buffers at a much higher resolution than they are displayed at on screen. So I think for a normal Oculus headset, and I think the same applies for the Vive, the resolution of the eye textures are actually twice as high as the resolution of the display itself. And that just purely has to do with that lens effect, because the center of the image is so stretched out that you need that higher resolution to actually still get get an acceptable level of quality. And therefore, I am taking that render buffer and I'm actually making it half the size to get my my window size down to something that actually fits on screen. And probably, as I'm going to be putting this video together with some of the in-game footage, I'm probably even going to crop that somewhat, because of course this will be an image that has a very it has a portrait orientation instead of a landscape orientation, which you would normally have on your display or on your desktop. Anyway, this is just a way to size that a bit better and get something on screen that we can view. The other thing to keep in mind is that to get the field of view to be perfect for the HMD, we're actually getting quite a stretched out image, and of course resizing that on screen like this is actually going to crop it somewhat. So you'll see that the image doesn't look right when it's on desktop. It looks perfect on the headset, but on the desktop it looks cramped. It looks like the aspect ratio is all out of whack. but again, that's just an effect of what we're doing here. The last thing that we need to look at as far as pure setup is concerned is in our project settings, and I always forget where this one is hiding. I think it's window display. Here we go. There we go. VSync. Notice that I have turned VSync off. And this is a very important thing to do when we are looking at using OpenVR or probably VR in general. When we are looking at rendering VR on a PC or on a laptop like this, rendering to the display alongside of rendering to the headset means that the frame rate will basically go down to the weakest one. So my laptop monitor will probably run at 60 frames per second. That's 60 hertz. And using turning VSync off will basically limit my frame rate to 60 frames per second. While the headset has no problem in handling 90 frames per second. To be exact, it actually has to run 90 frames plus to be comfortable for the wearer. So yeah, turn VSync off to enable rendering on full speed on the headset. There's actually a VSync in OpenVR itself as far as the output to the headset is concerned. So it won't give you any weird effects on the display itself. And as far as I'm aware, not on the main display either, unless you do some really crazy things. Anyway, that is the last of the normal settings. So as I said, the setup, it stays the same, and with all these basic steps, we have basically enough to run this game and have someone look around in our world. There's one more thing that I want to look at before we actually look at some footage, and that is the script that is on the player itself. Actually, no. Let's cut to the video first, and we'll get back to this after the game video or the game footage video finishes. So that was the demo of our little demo game, and as you can see from the video, we've only supported a few basic things just to get started, and to give us a framework to work on. So yeah, there's a couple of things that we need to talk about, and the first is obviously we are making a first-person game here, a little demo environment where the player can just walk around an open area, and that poses a few unique challenges. I was originally thinking about starting with like a driving game or a flying game or something like that, but I figured there's too much stuff to set up there that has got nothing to do with VR, even though that's a simpler implementation for doing VR. I decided not to go with that for our first demo. Instead, I decided to start with this. Now, if we were to build a space sim, for instance, where you're sitting in a cockpit of a some sort of ship, flying around an environment, we actually don't have to deal less with one rather annoying side effect in VR, and that is motion sickness. When you are sitting inside of a cockpit and you have the cockpit around you, you have the canopy through which you're watching, so you're seeing the sides of the canopy, you're seeing the instrument panels in front of you, you're seeing a whole bunch of things about the environment that you're sitting in. And as your spaceship is flying around, whatever environment you're flying around in, you're sitting stationary in relationship to the cockpit, and it is the whole ship that is moving through this environment. And that is enough for your brain to basically be happy with the fact that what it is seeing and what it is feeling isn't the same. But when we're looking at the environment that we have created here, where I am freely walking through a little forest, basically, all of a sudden we have to deal with one very annoying little fact, and that is that as I am moving through this world, I'm actually still standing still. So obviously, depending on whether you've got rule scale tracking, or in my case, I have a relatively small area that I can move in. I can take about half a step forward and backwards before I run into something. But it gives me enough room to freely turn around and bend down or and things like that, and move my arms around freely. But I can't really walk through a world physically, so I have to rely on some form of controller input to make my character move through my world beyond the confines of my tracking space. And as a result, I am moving through this virtual world without physically moving. And that is a problem. That is something that tends to be causing a lot of motion sickness with people, because what they are seeing and what they are feeling isn't the same thing. Now, when we are looking at what we have done here, I have started with the very first step. Obviously, I want to start looking at things like teleporting and some of the other locomotion techniques that are out there and seeing if we can reproduce them in Godot. But for this very first demo, I wanted to stick to the basics, to the assumption that you have someone who just has a VR headset and is therefore relying on controller input, either a gamepad or a joystick. It actually supports keyboard, but I don't think that is a realistic input device for VR, making that possible. Now, there's basically two sets of movements that we are currently supporting. One is the player turning around. So as you can see, actually in the code here, it's implemented through actions. We have a turn left action and a turn right action. That is for turning left and right. We'll look at the code in more detail in a minute. And then the two easier ones, which is the move forward and move backward actions. And these are all controlled with the first axis, the left axis on the very first gamepad. And for those people who are familiar with Godot, this will be no surprise. if you go to the input map in project settings, you will find these actions defined here. So here's our turn left, which is linked to our left key. Again, like I said before, that probably isn't very useful for VR, but for prototyping or demoing, or just running it on your desktop just to test something out, it is handy to have as a backup. And it is then taking your your left stick left input on your first gamepad device and your first axis as input. So if I just have a headset and I plug in a normal game controller into my my laptop, or everybody who's bought the Oculus Rift before the touch controllers came out would have had an Xbox One controller with the headset. They will be able to use that as the input for this environment. Obviously, if you turn this into a real game, you'd probably want to make that configurable. Someone might have the second controller that they want to use for it, or they want to use the right stick instead of the left stick, or something like that. But this is a good way to set up those defaults. There's a little segue there to another part of this. In the demo, you saw me using the touch controllers instead of a gamepad. I was waving the touch controller in front of the camera just for fun. And the touch controllers have got these little joysticks on the top. And lo and behold, we've made sure that those are mapped to the first axes, because every VR controller is both represented in the environment as an AR/VR controller node, but it's also available as a joystick. So every VR controller that gets enabled is also recognized as a joystick in Godot, and therefore you can use all the standard functionality around joysticks that exist in Godot. So first of all, it automatically means that our action pressed function works, because that's all supported, but you can also react to input events as you can with any joystick in Godot. So that was a nice way to have both this form of locomotion supported if all you have is a gamepad and you don't have the controllers, or if you do have the controllers and you want to use the little joysticky on the controller. And probably if you have Vive controllers, I'm expecting it to have the same functionality if you use the little touchpad things on the controllers. The only thing that is a problem right now with this is that the controller for which it uses the input is the very first controller that you turn on. If you turn your right hand on first, it will be on your right controller. If you turn your left hand on first, it is your left controller. With code, you can deal with that. Godot or OpenVR will actually tell you which controller it assumes is your left-hand controller and which controller it assumes that is your right-hand controller. With the Oculus Touch controllers, there's actually no question, because the controllers are differently formed. They are actually physically different for your left hand and right hand, as opposed to Vive controllers, which are exactly the same for your left hand and your right hand. It is just whichever one you pick up first is probably identified as the left hand or something like that. So you have to deal with that in code, and at this point in time for this demo, I thought that just went too far. I didn't want to get into that. I just went, the very first controller that you turn on, that's the one that we're using in our little demo here. Okay, let's start with the moving forward and moving backwards, because those are the easiest to talk about. Those are also the ones that the human brain has actually got the least amount of problems with. If you move to the direction that you're looking, your brain generally accepts that movement as okay enough. It creates the least amount of motion sickness. But as you can see from this little line above, we are actually using the global transform on the HMD, and the HMD is gathered here, which is the the actual AR/VR camera node in our player origin scene. It is using the global transform to figure out the direction into which the user is looking, and then zeroing out the Y component in that direction so that I actually have a direction on the horizontal plane. And it is in that direction that we either add or subtract the position of the player. Now, in this, there is another thing that is really important, and that is that while we're getting our global transform, our orientation from the camera, what we're actually changing is the translation on this root node. And if you might remember from looking at the origin, our script is linked to our AR/VR origin node. So it is actually the AR/VR origin node that we are moving around to move the player around. We are not moving the camera or any of the controllers because they are all automatically positioned by the tracking system in OpenVR. It is the lighthouses or the wrist cameras that are detecting the movement of the player and the orientation of the devices, communicating that back to Godot, and Godot in turn updating the position of all those components. So we can't change the position of those things. They will be overruled. We need to change the player origin. Now, for moving forward and moving backwards, that's really easy. As you can see, we just figure out what the direction is in which we want to move our origin point, and and we move it. But for rotation, that is a little bit more tricky. We actually need to do a little bit more because we actually want to rotate around the position of the camera, the position of the player, not around the origin point itself. And that is why this logic does what it does in first getting the location of the HMD, creating two transfer forms of that, and actually applying that in sequence. First moving the origin point to where the camera is, applying our rotation matrix, and then moving the origin point back and applying the original transform. And that will result in the origin point actually being rotated around the player center, and as a result the player moving around, which is what we want. But now for the last bit about that rotation, because I kind of skipped over that, but it is the important thing. And it is probably something that you might have been wondering ever since seeing the little video, like, why did he do that? I've actually got some feedback on Facebook from that. Anybody who's played VR games will have recognized it. People who've not played first-person VR games will probably go like, is that a bug? No, it's not a bug. The shaky turning around of the camera when the person turns around is actually done on purpose. Instead of a smooth turn of the camera to the left or a smooth turn to the right as you push your joystick left or right, we're keeping a counter which we increase by the time that has passed as long as our action is pressed. And we are only updating and rotating the camera if enough time has passed. And that means that instead of a smooth turn, we get a fixed turn every, I think it's set currently, it's currently set to every 0.2 seconds. So every 0.2 seconds, we turn the camera by 10 degrees. And it looks ugly. It looks weird and it looks wrong, but it's done for a very important reason, and that is that whole motion sickness problem. If we would be moving the camera smoothly, a lot of people very quickly get very sick, and it is because turning your head is something that your brain is really good at. When you turn your head to the left or your right, your brain is actually compensating what your eyes are seeing by the the physical turn of your head. It's one of the reasons why if you turn around a couple of times on your toes and you stop, you'll get dizzy. Your world still keeps on spinning. It's your brain compensating for the fact that it's actually still thinks that you're spinning, because the organ in your ear that measures your movement is still telling you that you're spinning. And we're doing the exact opposite of that. What we're doing is we are showing our brain that we are turning, while the organ in our ear tells our brain we're not. And basically you make people dizzy when you do that. Doing the step turn turned out to be one way to combat that motion sickness. Instead of having a smooth turn of your view, having this stepped turn of your view seems to help. It seems to reduce the motion sickness a lot of people experience walking through a first-person world. And this is just one example of how you could implement that. I'm not saying it's the best one. I'm not saying it's the only way to do it. But as a start, it seems to be working pretty well. Now, I've seen for a number of games that take this approach, which have this type of controller input, that they usually make this settable. Either turn it off, make it turn like this with a small step, or turn with a bigger step. Basically make the turn delay and turn angle something that the user can set. Obviously, here in this example, I've hard-coded that all. But yeah, that's definitely a good next step. I'm going to skip over it. I know that I'm going through this code in the wrong order, but I'm going to skip over this little bit of code. Although, if you read it, you probably can figure out what it does. I think that last one should probably be false. I'm not sure. We'll get to that when we're actually going to start using this code properly. Well, just to very quickly talk at least something about that. The center on HMD is a command that you can give the AR/VR server. It takes the current position of the headset and it makes that the center of the physical world. So it basically moves the player origin to wherever the headset is. This is incredibly important for space sims and that sort of thing, where you want to make sure that you ignore a lot of the tracking information. You just want to make sure, hey, I want that person's head to be here. End of story. But for a first-person environment as this, this key press space is probably not something we want. I left this in here purely for testing, but this is going to become a very important command once we start implementing things like teleport. The last thing that I wanted to mention about this piece of the code is that we're running this code in our physics process, which used to be called fixed process. It's been renamed in Godot 3.0. And that all has to do with timing. Running it in the physics process means that the positions are updated right before we start rendering, and that just turned out to give the best results. If you instead put this code into the normal process code, you get a lot of shocking as the positioning of objects tend to be a frame behind. So yeah, I'm still a little bit on the new side to Godot itself, so I'm pretty sure that some others in the Godot world can give you a much better description of what the difference between physics process and normal process are. But yeah, recommend definitely use physics process to do any updating of positions of the player to make sure that that you get very smooth results. Okay. I think that's it for today's video. Download the little demo application if you have an OpenVR installation on Windows, and have a play with it and give me some feedback. Hope you guys enjoyed this.